Right. Okay, so straight off the bat, you know it's got to be one of these two. Now, the reason you know it's got to be one of them two is because this is negative, but that's neutral. So something here has got to be positive to be making this neutral. So obviously that's got to be W+, which means we can definitely say it's not A or D. And then with the quark composition, you've obviously got your down, which is equal to -1/3, and you've got your up, which is equal to +2/3. So this guy is -1/3 +2/3 +2/3, which equals 1, which obviously means it's a proton. Now, if it's losing its positive charge, it's going to be going to down, up, down. So therefore, the answer is B. Right, so deduce the name of particle X. Well, if it's up, down, down, an up particle is 2/3, and a down particle is -1/3, which means if it's up, down, down, it's 2/3 plus, -1/3, -1/3, which equals 0. Therefore, it is a neutron. State type of interaction in this decay. Now, it's not asking what the decay is, so you can't put beta. The interaction is using a W boson, which means W equals weak. So it's a weak interaction. State the class of particles which the W- boson belongs to. Well, it's bosons. You could put exchange particles, so you can get away with that if you're really stuck. Show clearly how charge and baryon number are conserved. You should refer to all particles, including the quarks. So, with this one, obviously before you have up, down, down. So you've got 2/3 -1/3 -1/3. Oops. There you go. -1/3. And then obviously that turns into a up, down, up. So it's 2/3 -1/3 +2/3. So that here is showing that this on the left is equal to 0. And this on the right is equal to 1. Now, with the E minus, obviously you're going to have, you've got to conserve this. So if it's 0 this side, you've got your 1 on that side. So we've obviously got to have your -1, and then your neutrino is equal to 0. So it's +0. So you're showing that charge is being conserved here. Now, as well as that, with your baryon numbers, if you just bear with me, your baryon numbers on this side, with it being, these guys are being baryons. So you've got your up, down, down. In reference to your quarks, you've got your baryon number of 1/3, your baryon number of 1/3, and your baryon number of 1/3. And it turns into your baryon number of 1/3, your baryon number of 1/3, and your baryon number of 1/3 for the quarks. And then E for your electron is a lepton, so that's not a baryon, so it's 0. And your obviously your neutrino isn't a baryon either, so that's also 0. So that's also showing that baryon number is conserved as well as charge. Now with this, you can put 1 equals 1 + 0 + 0. You'll still get 1 mark, but it specifically asked you here, including the quarks, so you've got to say about the quarks as well. Name the only stable baryon. It's obviously the proton. You either know that or you don't, so if you don't, you need to learn it. And a muon is an unstable particle. State the names of the particles that are produced when a muon decays. Now, if you have a look at all our work we did on muons, the whole lesson, literally I ran through this. It can be an electron neutrino, or a muon neutrino. They're the only things that can decay into, so you just need to remember that, and then that will make your life a lot easier. Okay, so how many quarks does a sigma plus particle contain? Well, it's a baryon, which means it must be containing 3. Simple. How many quarks are strange? Well, it's got a strangeness as -1, So if it's one particle and it's got a strangeness of 1, there must only be one strange particle in it. Now, the sigma plus decays in the following reaction. So sigma plus is up, strange. So I'll do this down here. So it's up, strange. And it decays into a pion, which is an up, anti-down, and a neutron, which is up, down, down. So state 2 quantities that are conserved in this reaction. Now let's just make life a lot easier for you. So the charge on a sigma is 2/3 plus 2/3, that's a 3, minus a third. So its charge is 1. An up anti-down is 2/3. And then remember, if it's an anti-down, the charge flips, so it becomes plus a third. So that's 1. And then plus your neutron, which is a 2/3 plus a third. Sorry, minus a third, which equals 0. So you know that charge is conserved. And then you also will know that if here you've got a baryon, so its baryon number's 1, that's not a baryon, so it's not got a baryon number. And then its baryon number here is 1 because it's a neutron, so you know that baryon number is conserved. Baryon number. And then also, if you want to be extra vigilant, you can also make a note that the lepton number's conserved because there's no leptons there, if you really want to be picky. As well as that, anything that's in terms of conservation, mass, energy, and momentum. So worst case scenario, if you're really, really stuck, just say one of them 3. So state a quantity that is not conserved in this reaction. Well, here you have a strange particle, and here we do not. So strangeness is not conserved. So if your strangeness is not conserved, it must be the weak interaction, because the weak interaction is the only one where strangeness isn't conserved. So into what particle will the neutron decay? So what does everything eventually end up as? If it's a baryon, it will end up as a proton. Right, so complete the table by naming one example of each particle with a lepton. Easy peasy, just go for your electron. Oh, hang on. Baryon, protons, neutrons, proton, neutron. Mesons, you've got things like your kaons, your pions, so I will just go kaon. Now, the following reaction cannot occur. State and explain which conservation law is going to be broken. Right, so if we're thinking about baryons, so baryon, I'll make blue. Not a baryon, not a baryon. That's supposed to be a 0. Okay, so baryon number is conserved. So then if we look at the lepton number, I'll change the colour. Lepton number, that's not a lepton, that's not a lepton, that's not a lepton, that's not a lepton. So lepton number is conserved. So then if we have a look at, let's make that a nice pretty red, charge, you've got your pion, which is 1, and your neutron, which is 0. And then you've got your proton, which is 1. And then you've got your other pion, which is -1. So that's clearly the thing that's not being conserved. So if you demonstrate that and just say not conserved. Now, always double check everything, because if you end up saying something that's not conserved that is, then you end up losing all your marks, so just be really careful. So state and explain one conservation law that's not broken. Well, you've just shown 2 here, so you could say your lepton and you could just show that one, or you could say your baryon and you could show that one. Strangeness is also conserved, because obviously there's no strange particles going on there, so you could just put 0, 0, 0, 0 like you have with your leptons. Now, describe what happens when a proton and an antiproton collide. Well, that's called annihilation, which I always struggle to spell. And when that happens, obviously you're going to have a pair of gamma rays coming out. So if you have a look at our reactions again, it's a pair of gamma rays. You can get away with saying releases energy. on this question, but I've seen ones where that won't be enough, so you're better off, putting that instead. Right, so give the name of the nucleons and the number of electrons in an atom of sodium. So nucleons is anything that's in the middle, so that's your top number, which is 22. And your electrons is the same as your protons, which is that number, so that is 11. That's GCSE, so if you don't know that, you really need to start looking at your work. The isotope is a positron emitter. In a positron emission, an up quark undergoes the following change, which changes into a down quark. Show the charge, lepton number and baryon number are conserved. So with your charge, it's gone from being plus 2/3, and then it's changed into minus 1/3, and then it's plus 1 and plus nothing, because that is your electron minus, okay? Now, your lepton number is going to be 0, and it changes into 0, and then it changes into minus 1, because it's a positive one, isn't it? And then it changed into plus 1. So there we go. So it's conserved. Now, baryon number, you got your quarks. So obviously, baryon number on this side's 1/3, and then it changes into a 1/3. And then this is a lepton. So that's nothing, and then that's a lepton, which is also nothing. So that shows a conservation as well. Describe what happens when positron collides with an electron. Again, this is annihilation. And then with annihilation, you get your gamma rays. You can put photons. Are produced in a pair. And with this, they actually also expect you to mention something else as well. You can get 2 marks. That actually gives you 2 marks, but just as something else you can say, you have to mention maybe that your mass is conserved and converted into energy. Because that follows your E0 equals mc squared rule, okay? So there we go, that's how we do that one. Okay, so K negative has a strangeness of -1. Now, if you remember, it's -1, which means it's an S particle, okay? So write down its quark composition. Now, kaons always have a strange particle in them anyway, whether it's strange or anti-strange. So if this is going to be -1, you know it's got to have an S in it. And then for it to conserve the charge, it has to be an anti-up, okay? Now, the kaons K0 and K plus both have a strangeness of +1, so you know they've got to have an anti-strange there. So you got your anti-strange and your anti-strange. And then, again, you just need to make sure that you're conserving your charge. So this one is going to be a down anti-strange, and that one's going to be an up anti-strange, okay? Now, write down the quark composition of a proton. I just recommend you memorise this because it comes up all the time. So it's up, up, down, okay? And neutrons, again, I'd memorise, which is up, down, down. Now, in this strong interaction, deduce the quark composition of and state the hadron represented by X. So if it's a hadron, you know it's got to have 2 or 3 particles in it, okay? Now, deduce the quark composition. So if it's K minus, it's gone from strange anti-up, and then you plus in your up, up, down, turns into down anti-strange plus up anti-strange, and then plus RX, which we don't know. Now, straight away I can see something's dodgy here because I've got 1 strange here and 2 anti-strange there. So that's clearly the indicator that that's something to do with what we're trying to find. So if the strangeness on this side is -1, and then we look on this side and it's +1, +1, then obviously here our strangeness at the moment is +2. So this value here needs to be -3, so it's strange, strange, strange. And there we go. We found something with 3 particles. It conserves our strangeness. Now we know our strangeness has to be conserved here. It's a strong interaction. The only time strangeness isn't conserved is if it's a weak interaction. Now, positive muon decays into a positron and 2 neutrinos. So we've been told what's actually, we're writing it in. So write down the equation. So you've got, it's gone into a positron and 2 neutrinos. Now, again, I mentioned this earlier, your 2 neutrinos almost always are your electron neutrino and then your muon neutrino. But the thing is, you've got to work out which one's going to be the antiparticle. So, you know, you've got the plus and the plus there. So that's where we're going to be at with that. These are both 0, but because it's a muon, that's going to be your antiparticle. Okay, so here we have, it said that you got your pi negative and a proton collide and were annihilated and created that, and that. Write down the equation that represents this. So it is literally as simple as you have pi negative plus a proton makes a neutron plus a pi positive plus a k negative. Done. Easy peasy. Okay, so just read the question properly. So show in terms of conservation of charge, baryon number and lepton number that this transformation is permitted. So with your charge, we've got -1 because of your negative pion, plus your proton, so that's +1, turns into neutron is neutral, +1, -1, so that's conserved. Your baryon number, well, pion's only got two quarks, so that's not a baryon. Proton's a baryon though. Neutron's a baryon. Pion, as we just said, is not a baryon, and kaons are not a baryon. So there we go. It is conserved. And then your lepton number, pions are not a lepton, protons are not a lepton, neutrons are not a lepton, pion's not a lepton, kaon's not a lepton. Easy. Okay, so there we go. You have just proven that these things are conserved.